Okay, welcome to the first module in EDRM 706 on power analysis. Power analysis, really just the concept of power, can be a little bit difficult for students to understand. So as we go through this lecture, I'm going to give you some more statistical lingo types of definitions, and then I'm also going to try to break it down so that you can maybe visualize what is meant by power. Okay, what is statistical power? All right, in the stats lingo, this is the probability that a statistical test will reject a false null hypothesis. Okay, so again, it's the probability that we will reject a false null hypothesis. But that's terrible, right? What does that really mean? What it really means is it's the probability of detecting an effect or a difference, given that the effect or difference is really there. And so as I talk about power through this lecture, I'm going to consistently use the term effect, which here is synonymous with a statistical difference. So if it's easier to think of this in terms of like two means being different, that might help as you go through this. So again, where are we on statistical power? It is the probability of detecting an effect, given that that effect is really there. Okay, and power is related to how big of a difference exists, like what is the size of that effect or magnitude of that effect, and then it's also related to the sample size. We use a priori power analysis to estimate an appropriate sample size for our studies. So a priori means before we have done anything related to our study, prior to data collection. So before anything has started. And if the sample size is too small, we may not detect an effect. All right, so this is the issue with sample size. So when you go in and you say, hey, I want to conduct this study where I want to look for this difference, the number one thing you'll hear from colleagues, from grant funding agencies, from reviewers of manuscripts is, how do you know if your sample size is adequate? Did you conduct a power analysis? All right, and so again, oftentimes reviewers ask for power calculation evidence to justify the sample size you used. And then also grant agencies, especially federal grant agencies, so National Institute of Health, National Science Foundation, they are going to ask for a power calculation to justify the proposed sample size in your grant. All right, so let's dig in a little bit to power. And so we're going to go through a few slides where we're working with this graph on the right, and we're just going to break down each component that you're looking at. All right, so we know from our previous stats class that H naught is the null hypothesis, which assumes or tests the absence of an effect, right? It would always, like in terms of mean difference, it would be that there is no mean difference or the two means are equal. If we're thinking about an ANOVA across 3 or 4 categories, that omnibus test would be testing that all those groups have equal means. And then we have the alternative hypothesis, which says that an effect exists, right? Or that a difference exists. So a simple example that we could think of with this would be that maybe we are interested in comparing math achievement scores between boys and girls. And so the null hypothesis would assume that the average math achievement score for boys and girls is the same, is equal, and the alternative would look at maybe that the boys' mean achievement score is greater than the girls' mean achievement score in math, and so there we see that that the purple alternative hypothesis distribution shifted to the right, signifying that the boys are their distribution is higher than the girls' distribution. And it's worth noting here that in this very simplified example, that we are assuming these distributions look similarly. They have the same shape. In other words, the standard deviation would be the same for boys and girls here in terms of math achievement. All right, so we've got an alpha down there on the bottom. Do you really remember what alpha represents? Hopefully you remember from EDRM 705 something referred to as the type 1 error rate. And the type 1 error rate is the failure to reject a true null hypothesis. And so then alpha is the probability of claiming an effect that is not there. Okay, so you can think of the t-tests and ANOVAs from EDRM 705, and if alpha was set at 5%, that 5% represented the probability of claiming an effect that is not there. So falsely claiming an effect or falsely concluding that difference. All right, and so how does p-value relate to alpha? So alpha is kind of where we're saying, okay, so this is our minimum probability that we're willing to accept for claiming an effect that is not there. As you know, we tend to use 5%, but certainly sometimes we can use 1%. And then the p-value is the probability that the observed effect occurred by chance alone. Okay, so eek emoji, what does this really mean? All right, it's the probability that a difference as big as the one observed could be found even if there is no effect, right? So really it's that p-value is the probability you've made a mistake in your observed data, rejecting the null hypothesis. That's why we want p-values very, very, very small. So when that p-value is less than 0.001, we're happy, right? Because that means there's less than a 0.001 chance that we're making the wrong decision here by rejecting the null from our observed data. Okay, what about statistical significance? All right, so you should remember this idea of confidence or confidence intervals. Confidence, okay, so if there is in fact no statistical difference, we accept that there is a chance that we do observe a difference, right? Because let's look at our two distributions here. They do overlap. Even though we see these distributions separate from one another, we see that the means, the mews, the population means are different from one another. They still overlap, right? And so if we are randomly drawing from our population in this area where they overlap, then it's reasonable to think that in our data, in our sample, we're not going to observe a difference, even though here in this situation, we have our eyes on the population and we're able to see that there is a difference. So what does 95% confidence mean? It means that there's no more than a 5% chance of making a mistake or a type 1 error. All right, and then how does this compare to statistical significance? Comparison between alpha, usually 5%, and the p-value, all right, is when we start talking about statistical significance. All right, and so here, if we're setting that alpha, okay, our probability of making a type 1 error, if we're setting it at 5%, then we compare our p-value to 5%. And if the p-value is smaller than 5%, then we reject the null, and we're concluding here that there is a difference. And if the p-value is greater than 5%, then we're concluding there's no statistical difference and we fail to reject the null hypothesis. Similarly, if we use 1% as our alpha, then we're comparing our p-value to that 1%. Okay, what about type 2 errors, often referred to as beta, and power? So this is something that wasn't discussed much in EDRM 705. We talked briefly about comparing type 1 and type 2 errors, but a type 2 error is the failure to reject a false null hypothesis. Okay, so again, it's we didn't detect an effect, but an effect is really there. All right, and so beta is the probability of missing an effect which is really there. So alpha is the probability of rejecting the null when we shouldn't. Beta is the probability of failing to reject the null when we really should. Okay, and power is the probability of detecting an effect which is really there. So you should, like right away, when you're looking at these two definitions of power and beta, you should see a complementary relationship. All right, and so there is a direct relationship between type 2 errors and power, in that power is simply 1 minus beta. All right, so big question, how much power do we need? All right, the rule of thumb, the general convention is 80% power, but it could obviously be more than 80%. And I say 80%, the general convention when you're responding to reviewers for a manuscript, or you're running a power analysis for a grant proposal, typically in those situations we'll use 80%. But sometimes you want more power. You want to, maybe figure out what the sample size needed is for, say, 90 or 95% power. Okay, and again, let me go back for a second. 95% power would tell us there's a 95% chance of detecting an effect, which is really there, right? That we want that. We want to detect an effect if it's really there. All right, and so if power's 80%, then beta, the opposite of that, is 20%. All right, and so when we're working with that 80% power level, it implies a true difference will be missed 20% of the time. Are we okay with that? Are we okay with missing a true difference 20% of the time? 1 out of 5 times that we would potentially conduct this study. Again, this is one of those things in statistics where that 80% does get used as the rule of thumb. But I think we could all argue that it would probably be better to be working with 90 or 95% power. All right, so where does 80% come from? Is it completely arbitrary? To some extent. Jacob Cohen, all the way back in 1962, wrote a manuscript and saying that for most researchers, type 1 errors are 4 times more serious than type 2 errors. And that is where we get 20%, because we take our standard alpha of 0.05, we multiply it by 4, and we get this somewhat arbitrary beta of 20%. Okay, so let's just talk about, sampling our distribution. So we've got a population of girls' math achievement scores. We've got a population of boys' math achievement scores, and I've still got the little graph up there at the bottom. And think about just random sampling from we'll just call, for right now, for sake of argument, we'll call the red one, the red curve, the girls' distribution, and that purple or blue curve, the boys' distribution. And so if we look at the very first graph on the left side, all right, as I mentioned before, we could randomly sample in that overlapped area, right, where these two curves overlap. And so if we randomly sample where these two curves overlap and average, right, the boys sample and average the girls sample, and then statistically compare these two averages, we see something like we do on the left, which is these means are not very different, and we see the error bars, or these are 95% confidence interval bars, that they're not different from one another. They overlap. And so what this is telling us is that there isn't a significant difference between average girls' score in math achievement and average boys' score in math achievement. And if we keep, and let's just, because we're controlling this experiment, let's, start random sampling from a little bit separate areas in the distributions. And so then we move to the next graph, right, where that difference grows a little bit more. And then gradually, as we move across the screen, across these 6 bar charts, we're seeing that the means get greater and greater. And so by the end, this here in the far right graph, we have sampled from the girls' distribution in an area that really doesn't overlap much with the boys' distribution, and then we have sampled from the boys' distribution that really is more separate from the girls' distribution. And what we see is that the confidence intervals do not overlap, signifying a significant difference between average girls and boys' math achievement scores. All right, and so again, as we move across, we go from this small difference where really no significant difference is observed, over to the right where a big difference is observed. All right, and so you can see on the graph at the bottom this line that goes through the 2 graphs that says critical value. All right, so what is critical value? Critical value, and I have continued to draw it up here with this kind of gold dashed line. The critical value signifies where the p-value changes from not significant to significant. And so the 4 graphs on the left of the critical value line all have overlapping confidence intervals. They would not be considered significantly different. In other words, they would all, when comparing these 2 means, all the p-values would be greater than 0.05. All right, so we would fail to reject the null in that situation. However, on the right of our dashed gold line, or the right of the critical value, we see significant differences. We see p-values smaller than 0.05. So in these 2 situations, or in these 2 samplings, we would reject the null. All right, and so the $1 million question is there an effect or is there not an effect, right? Well, again, we have the very atypical situation here of being able to look at our distributions and observe a difference between these distributions. And so power's coming into play here. Notice for each of these that we're only sampling 6 boys and 6 girls each time, all right? So what is affecting this critical value, all right? And the critical value is affected by the size of the difference, the magnitude of the effect, okay? How different are these 2 means, let's say? The sample size and the significance that we're using, all right? So obviously 0.01 as an alpha really pushes that gold dashed line, that critical value, further to the right, okay? Sample size, the larger of a sample that we grab from our populations pushes that critical value, or the gold dashed line, more to the left, all right? And the size of the difference, the more different the effect is, that also pushes the critical value to the left, much like a larger sample size. Okay, so if we want to conduct a power analysis, what is needed? All right, as I mentioned, we're going to need the effect size, all right? So hopefully you remember this from EDRM 705. And we need the desired power of the study. Example, we've been talking about the rule of thumb of 80%. We need alpha, we need our significance level. Again, we tend to use 5%. We need a sample size, and we need an alternative hypothesis, meaning we need to know if we're running a one-tailed or two-tailed test. So in other words, are we testing for a difference, which would be two-tailed, or are we testing, like in this situation, boys greater than girls, which would be a one-tailed test. Now, I quickly skipped over that first one, effect size, but I'm guessing we should probably review this. Okay, so effect size. Effect size measures the strength of the relationship between two variables or the magnitude of the differences between two means. Typically, we are referring to the standardized measure of effect. You can look at unstandardized measures of effect. So an example of an unstandardized measure would be the unstandardized slopes in a multiple regression line. But typically we need standardized measures. So this would be like little r here, Pearson's correlation, or Cohen's d, which you used with t-tests in EDRM 705. All right, so why do we need standardized measures? First and foremost, the metrics of variables do not always have intrinsic meaning. You can think here like a simple one here would be SAT score, like SAT math. What does that value really mean? What does the number really mean? Sometimes when we use ordinal Likert scales, there may be some intrinsic meaning there from maybe like strongly disagree to strongly agree. But a lot of times we do have variables on metrics that have no meaning to us. Variables also very often in our models use different scales, right? We may have motivation on a 6-point Likert scale, and we may have math course grade, which is on a 0 to 100 scale. And so we need to standardize here to be able to compare apples to oranges. And then also, sometimes we want to be able to compare our results in our present study to results from other similar studies. For example, if we're running let's just gross motor development intervention for preschoolers, and there's a curriculum out there called SKIP, which is Successful Kinesthetic Intervention for Preschoolers. So it develops gross motor skills. And we have multiple studies where we have looked at the effect of SKIP on gross motor development. Then we always want standardized effects so that we can interpret across our studies. Okay? And just as a reminder, when we refer to a standardized measure, what we're doing there, it's kind of like converting numbers to z-scores, where we're going back to being able to interpret in terms of standard deviations. Okay, and so here simply with Cohen's d, we see that as the difference or the effect gets larger, the distributions move further apart. So that's kind of what we mean by standardized effect. Okay, so let's just review just a couple examples of effect size and our typical cutoffs, because we're going to need to reference this slide a few times in the example in the lecture and in the classwork. Okay, so Pearson's correlation, as you should recall, is used for continuous variable, right? So we are looking at the linear association between two continuous variables, and it varies in magnitude between -1 and 1. All right, and typically with effect size, a standardized effect size, we're always looking at the absolute value. And in social sciences, we consider a correlation of 0.1 to be a small effect, zero point 0.3 to be a medium effect, and 0.5 to be a large effect. All right, Cohen's d, as you know, is used with t-tests. So it's the difference between two means divided by the standard deviation. All right, and you can see the table here I've provided that goes from a very small effect of 0.01 all the way to a huge effect of 2. Usually when conducting power analyses, you work within that small to large range, small being 0.2 up to large being 0.8. And then we have Cohen's F, which is used with ANOVA. All right, and it's the estimate of proportion of variance explained by a categorical variable. All right, and this is new, but the symbol that you see in the formula here, so under the radicand, you see an eta squared. And eta squared you should remember from an ANOVA. So when we run an ANOVA in JASP, we're going to get this eta squared as an effect size on our fixed effect. All right, and so we can calculate Cohen's F by taking the square root of the proportion of the effect divided by 1 minus the effect. All right, so let's go to an example now with G-Power, and let's start with a t-test. All right, what sample size is needed to detect a difference in boys and girls math scores? Okay, so, and this is the window you get for G-Power. All right, and first of all, the first thing we have to decide, all right, is the test family. All right, and so we have one continuous dependent variable, which is math scores, across two groups, boys and girls. And so this is a t-test. And when we look at our options for the statistical test under t-test, we would want to look at, we need to decide, do we have two independent means here or two dependent means? And so here, boys and girls would be independent. Remember, dependent would be like a before and after, or pre and post kind of test, where we kind of have that two repeated measures on a person. All right, and here we're only interested in a difference in boys and girls math scores. So we would want to change the tail here from the default of 1 to 2, all right, because again, we're just interested in a difference. All right. And then effect size, you know, this is where we're going to, it's not a wild guess. If you're writing a grant proposal or a paper, you're using historical studies or literature review, meta-analyses. There's lots of things we can look up now to kind of give us a ballpark for an effect size for what we're studying. And so here I say, is there a theoretical or typical effect size? For example, motivation tends to have a small effect size on student achievement. On the flip side, we see that formative feedback, you know, from the teacher, feedback has actually a large effect size on student achievement. And so this is where we would need to, if we're writing a paper or writing a grant proposal, we would need to do a literature review to have an estimate here of what the effect size is. On the other hand, if this is an intervention that we have run before and we're just running an intervention maybe under some new conditions now, we can certainly use the effect size we've observed across our studies before with this intervention. For example, the SKIP motor development intervention I mentioned earlier tends to have a large effect on children's motor skill development. All right, and we want to put in our alpha, all right, which is 0.05, or we'll just typically use 0.05 as our significance level. All right, and again, power, The program defaults to 0.95, but again, let's just for right now go with our general rule of thumb of 80%. And then the allocation ratio is the ratio of population sizes. So for example here, boys and girls, roughly 50% of the entire population. So it's a 1-to-1 ratio. All right. And so here I've actually run everything and I went ahead with the effect size of going with a effect size of 0.3, which is somewhere between the small and medium effect size of gender, the gender difference in math achievement. All right, and what we see, all right, so again here, we're assuming a relatively small effect size, and what we see is that if we wanted to conduct this study, we would need 352 students. We would need to sample 176 boys and 176 girls to achieve 80% power. Okay. All right, what if we, in our literature review, we see that there's actually more of a true medium effect size for the gender difference in math achievement scores. And so what happens if we change, and I'm going to go back. So here our effect size is 0.3. What happens if we change that effect size to 0.5? We see now we only need 128 students, 64 in each group. So the larger that effect, the smaller the sample size you need. All right, and then let's change the question a little bit. So now let's think, okay, what sample size is needed to detect that boys' math scores are in fact higher than girls' math scores? So what's changed here is instead of just looking for this kind of difference on either side, now we're like specifically looking at, you know, boys being higher than girls. So we're changing this to a one-tailed test. We'll keep our medium effect size. We'll keep our 80% power. All right. What happens to, and that should say medium effect size. What happens to the sample size now? Well, now it drops even lower to only needing 102 students, 51 in each group. All right. So again, going from a two-tailed test to a one-tailed test, when you know the difference, you can get away with a little bit smaller sample size. All right. Now, sometimes you'll hear about post hoc power, and every once in a while you'll get a reviewer who asks you to run a post hoc power analysis, in particular if you have non-significant results. And so let's go through this. Can we determine our power after we run our analyses? Yes. And I've given you guys a couple of post hoc power calculators for t-tests and regression, where your input becomes your results. All right. This is often referred to as retrospective power or observed power. All right, and this observed power is the observed effect size based on the sample size and parameter estimates derived from the data. All right, so hopefully you're seeing a little bit of a circular loop here that could be problematic. All right, and the idea in this post hoc power analysis is to show that a non-significant result was not significant because it lacked power. All right, so your goal here is to, use your observed effect size and your parameter estimates and get this retrospective power of 80% or bigger so you can say to a reviewer, the study was appropriately powered. All right. For a t-test, you would enter your observed effect size, your significance level, and a sample size. Now, big question. Should we determine our power after we run our analyses? And the big answer here is no. Simulation studies have found post hoc power analysis to be flawed. It's also theoretically flawed, right? Because post hoc power calculations are completely determined by the p-value, right? But if you have a high p-value, all right, and in this situation, a non-significant result, you'll always have low power. And low p-values will always have high power. All right, so we've just got a little bit of a, it's a little counterintuitive. And in the end, most people will say, well, post hoc power doesn't really tell us anything new. All right, and so nothing new was learned. All right, at this point, we're going to go to the classwork.